This video explores the chemical choices we make every day, focusing on the concepts of acids and bases. If someone suffers from acidity after overeating, which remedy would you suggest? Lemon juice, vinegar, or a baking soda solution? The sour and bitter tastes in food are due to acids and bases, and the correct remedy relies on understanding how they neutralize each other. Indicators are substances that reveal if a solution is acidic or basic, often through a change in color. Natural indicators include litmus, turmeric, and red cabbage leaves. Synthetic ones include phenolphthalein and methyl orange. A core rule is that acids turn blue litmus paper red, and bases turn red litmus paper blue. Acids react with metals to produce a salt and hydrogen gas. The experiment shown involves adding dilute sulfuric acid to zinc granules. The resulting hydrogen gas can be confirmed by the, quote, pop test, where a burning candle produces a characteristic pop sound when placed near the gas bubbles. The effervescence test differentiates acids from carbonates and metal hydrogen carbonates. The reaction produces salt, carbon dioxide, and water. When dilute hydrochloric acid reacts with sodium carbonate, the evolved gas is passed through lime water. The lime water turns milky, confirming the gas is carbon dioxide. Neutralization is the balancing act between acids and bases, producing a salt and water. The effect of the base is nullified by the acid and vice versa. For example, hydrochloric acid and sodium hydroxide react to form sodium chloride and water. The unifying principle is that acids produce hydrogen ions, H+, and bases produce hydroxide ions, OH-, in an aqueous solution. An experiment with an acid solution shows that the glowing bulb indicates the flow of electric current carried by these ions, unlike a glucose solution. Water is essential for acid properties. In dry conditions, dry HCl gas does not change the color of litmus paper. In aqueous conditions, an HCl solution turns litmus paper red. The separation of H+ ions requires water, where they combine to exist as hydronium ions, H3O+. The pH scale decodes chemical strength by measuring hydrogen ion concentration. A pH less than 7 is acidic, 7 is neutral, and greater than 7 is basic or alkaline. The scale ranges from 0 to 14, illustrating the strength of various substances like lemon juice and milk of magnesia. Acids are not all created equal. Their strength depends on the dissociation of H+ ions in solution. Strong acids like HCl completely dissociate, resulting in a lower pH. Weak acids, like acetic acid, only partially dissociate, leading to a higher pH for the same concentration. The world is highly pH sensitive. Aquatic life thrives in a narrow pH range, threatened by acid rain. Agriculture requires specific soil pH for healthy growth. Human biology functions optimally within a narrow range, relying on acidic conditions in the stomach. Even planetary science, like the atmosphere of Venus, is pH dependent. The pH of daily life is critical for digestion, tooth decay, and stings. Our stomach's hydrochloric acid aids digestion. Antacids, which are mild bases, neutralize excess acid. Tooth decay starts when mouth pH drops below 5.5. Honeybee stings inject acid, relieved by applying a mild base like baking soda. The nature of salts is hidden. The pH of a salt solution depends on the strength of the parent acid and base used to form it. Strong acid and strong base create a neutral salt. Strong acid and weak base yield an acidic salt. Weak acid and strong base form a basic salt. Common salt, or sodium chloride, is a raw material for a chemical empire. It is obtained from seawater or rock salt. Sodium chloride is central to producing substances like bleaching powder, sodium hydroxide, washing soda, and baking soda, all essential for daily use. The chlor-alkali process deconstructs brine, an aqueous solution of sodium chloride. When electricity is passed through the brine, it decomposes into sodium hydroxide, chlorine gas, and hydrogen gas. These products are crucial for industries ranging from water treatment to fuel and detergent production. The secret in the crystal is the water of crystallization, the fixed number of water molecules in a salt's formula unit. Examples include copper sulfate, which loses its blue color upon heating as water is removed. Plaster of Paris, a hemihydrate, reacts with water to form gypsum, used for casts and decoration.